Okay, so let's get into Chapter 12, Analysis of Variance. And the objectives here are to use the F distribution. So far we've used, when we look at business statistics and quantitative methods, we've used the Z and the T. Now we're introducing the F distribution. Okay, so this is when we're dealing with one of two things. Either two population variances are equal, or we're dealing with more than one mean, or more than two means at one time. And you'll see what I mean in a moment. So testing the hypothesis of two equal population variances. Now keep in mind we're talking about variance here, and we're not talking about mu. Okay, so when I say variance, right, I'm talking about that as opposed to this. Okay, so that's one of our takeaways there. We're using this to test hypothesis of equal population variances, used to simultaneously test the hypothesis that several population means are equal. Okay, so here we go. Here's our variances. The null hypothesis being that the variances are equal, and then you have the alternate hypothesis stating that they're not equal. So just in terms of being equal, right, we're just talking about this area here, and we're saying two variances are equal. So if we go down to this example, two Barth shearing machines are said to produce steel bars of the same length. The bars, therefore, should have the same mean length. Okay, so this is the mean right there. We want to ensure that in addition to having the same mean, they also have similar variation. So we're not just talking about the shears being, or the steel bars being the same mean length, average of 5 inches, let's say. We also want to make sure that they don't vary too much. So when you produce each one, you don't want them to go from 5 to 6 to 7 inches or 4 to 5 inches. You want them to all be around 5 inches. So that's what we mean by variation, right? So if we're looking at, multiple steel bars being produced, you want all of them as close as possible to the set mean. So that's different than what we've done before, right, where we were looking at means being equal. Now we're looking at variances, okay, being equal. All right, any questions on that?
No.
All right, so we get into our example here, and we can see Lammer's Limos offers limousine service from the City Hall in Toledo to Metro Airport in Detroit. The president of the company is considering two routes. One is via US 25, so if we're talking about US 25, we're going right there. And the other via I-75, okay? He wants to study the time it takes to drive to the airport using each route and then compare the results. He collected the following sample data, which is what we're talking about, right? This is our sample data, which is reported in minutes, okay? So they took a number of samples, and for example, 52 was how many minutes it took to go from US 25 to Metro, from Toledo to the Metro Airport in Detroit. 67 minutes the second time around, 56 minutes the third time around, etc. But if you take I-75, right, the first time was 59 minutes, second time was 60 minutes, third time 61 minutes. So using an alpha of 0.10, is there a difference in the variation in the driving times for the two routes? Okay, so that is our setup. So here it is, right? Very simply, first thing we see here is, right, our mean. And we're just saying if we add up all the drive times and divide them by 7, where do we get the 7 from? The 7 comes from the fact that there are 7 of these. So 1, 2, 3, 4, 5, 6, 7 for route 25. And then we have 8 for the other route. Okay. And the average was 58.29. Okay, going from point A to point B using route 25, and then the average was 59 using route I-75 going from point A to point B. if you put all of this data into Excel, or if you calculate your variance, okay, you would see 80.9 and then 19.1. And of course the S over here, that's our standard deviations. Square root of the variance is your standard deviation. Okay? All right, any questions so far?
No.
Okay. Okay, so state the null and the alternate. What we're stating here is what we said before, that the variances, okay, right here is a variance, right here is a variance, are equal. The variances are equal, and then we see the variances on the alternate hypothesis are not equal. So that's all we're stating, that they're equal or they're not equal. And again, we're not talking about mu's, okay, we're talking about variances. Number 2, we have an alpha, right, of 0.10, and then select the test statistic. That is step 3. State the decision rule. The F-stat is computed as the ratio of 2 variances. The numerator is always the larger of the 2 variances with its corresponding degrees of freedom. So if we look at, let me see here, F, right, we know it's a two-tailed test because it's an equals. Okay, that's the first thing. We know it's a two-tailed test because we have an equal sign right there. And we also know that we have an alpha. What was our alpha again?
I think 0.10.
0.10. There you go. So we have this 0.10 divided by 2 equaling 0.05. Okay, and that is the 0.05 right there. So that's what we're talking about. Alpha of 0.10 divided by 2 is 0.05. Okay. Now the question is, where do we get these other numbers? What is this 7 minus 1? What is this 8 minus 1? Okay. So 7 minus 1 represents the fact that there are 7 samples associated with the number, or with the set of data that gives us the highest variance. Look at this language here again. The numerator is always the larger of the 2 variances. Okay, this is our V1 is our numerator, V2 is our denominator. Okay, so we can say V1, no, don't say that, numerator, and V2 denominator. Okay, so now how do we identify which set of data we should be using as our numerator? Well, it's the set of data that has the larger variance. Okay, we cannot always assume that our numerator will always be the data that is on the left side, right? The only assumption we should be making is that our numerator will be the data that has the higher variance. So when we look at these two numbers here, right, or I should say these 2 variances, which one is higher?
Well, 25 variance.
Right, and what is the variance?
8.9947.
No, that's your standard D.
Oh, okay. The 80.990.
Right, exactly. So the 80.9, that's going to be the variance for US Route 25, and then 19 is going to be the variance for Interstate 75. So we can clearly see then that the US Route 25 has the higher variance. Okay, so if that's the case, then we can say, well, let's ask how many N's are in the data. Okay, what's the sample size of the data with the highest variance? Well, we know we're going to be using US Route 25 data. So what's the sample size of US Route 25? What's the N?
7.
Right. Okay, and that's very simple because we just look. We look right here. Move this down. We look right here, and we count an N of 7. So if we count an N of 7, then we use that 7 right here to identify our numerator, okay? And we're using the f-test in this way. We're saying that the numerator is always the larger of the two variances. So we've established that's US 25 data. And we've established that there are 7 samples in US root 25 data. And so we take 7 minus 1. And 7 minus 1 gives us that 6 right there. And then if you look at the other data, I-75 data, they are 8n, right? Our n equals 8. So we take 8 minus 1 and we get 7. So that's how we conclude, right, where we are looking for our critical value, or how to find our critical value. Okay? Any questions on that? Now, I haven't gone into a table. I haven't used Excel, but any questions on how we got at least to this point?
All right.
No.
Okay.
So it's basically just the highest variance that is the one that you determine which is the numerator.
Correct.
Okay.
And so again, what was the variance for US 25?
80 point something.
Right, 80. I think it was the 80.99. Okay, and if US 75 had, you know, a higher number, a higher variance, then we would have just used, you know, let me put it over here. We just would have used the 8s over here instead of the 7. Okay, so that's something that you got to keep in mind, something that you just have to remember. Okay, all right. Now, like I did last week, I'm going to go straight to Excel in terms of computing our F. Keep in mind that the F we're looking for will be 3.87. Okay, which is let's see here, which is right there. Okay, so let me show you how to find this. Now I have my Excel screen up. What I'm trying to show is f.inv, actually, equals f dot. Okay, 0.05, 6, and 7. And that number is going to be 387 if I round it to decimals. Okay, and I'm going to use this button here to show the rounding. Okay, so instead of using your table, you can quickly utilize Excel and that formula to better understand, or at least to get that 3.87 quickly.
Does it matter how do you put the degree of freedom in that?
Oh yes, oh yes. If you put 7 and 6, right, totally different number.
Okay.
Okay, so that's why you know, it's very important to identify which set of data has the highest variance.
Okay.
Which set of data has the highest variance, and then once you get that information, you say to yourself, okay, what's the n of that set of data? And in this case, the n was 7 because there's 7 data points, and so then you just go 7 minus 1.
Okay.
Okay, to get the 6. And then you say, okay, what is the n of the other set of data, the one that has the lower variance? And in this case, it was 8. And so 8 minus 1 gives you the 7. Okay, so that was our F points, our F with an alpha of 0.10, and then 6 and 7. All right, so ultimately our decision rule, right? Because that critical value of F of 3.87 just establishes the region known as the rejection region. So if I were to graph this, or to write the table, right, have my 0 here, 8, 7. Okay, and once we do that, we can then ask the question, what is the computed F? And for the computed F, right, we got to know this right here. And all that is that's just going to be your variance over variance, okay, 80.9 over 19, and that's it. Very simple to get your computed F if we're dealing with the testing hypothesis of two equal population variances, okay? So that computed F right there would be compared to the 3.87, and so I could put that right here, 4.23. And of course, this is the rejection region, and the 4.23 is in the rejection region. So ultimately, right, we will decide to reject the null hypothesis. Okay? Again, we're going to reject the null hypothesis because that 4.23 falls in the rejection region. Okay, any questions there?
Do we still use that same graph, the mu graph, rather than the F graph when we determine, or that doesn't really make a difference?
The mu graph instead of
The other graph that you just used, and then the F graph is like a one tail.
Oh, like this here?
No, just that one-sided.
Oh, okay. Yeah, basically it's just going to be this side, right? It's just going to be this side.
Right.
So the F family, right? It's still. Let me bring it back to. It's a family. It's still a family of distributions, but it is a right-sided family right here. So basically, we're just looking at this side of the graph.
Okay.
Okay, so back to our conclusion. This 4.23, right, falls to the right of the 3.87. So the data suggests that we should be rejecting, okay, the null hypothesis. And so if we look at this last piece here, there is no difference, or I'm sorry, the data indicate that there is a difference in the variation, okay, of the travel times along the two routes. And how do we get to that conclusion? Well, it's because we had this as our null, right? This is our null that the variances are equal, and we go ahead and we reject the fact, right? We don't like that fact that the variances are equal. Then we must not reject the alternate, which is that they're not equal. Okay, so if they're not equal, that means there's a difference. Okay, if the variances are not equal, that means there is a difference in the variation of the travel times. Either they're equal or they're not. Which one did we choose? The fact that they're not, which is H1. It's H1. Okay, any questions? Okay, we could also take that same data and plug it into Excel. This is just like in Chapter 11. And compute this information with the F-test to sample for variances. Okay, so all you would do is you would grab the data, right, drop it into Excel, and then do you would click on data, and then instead of, say, descriptive stats or something like that, you would select this test here. Okay, and once we get to the homework, I'll show you an example like this. And again, you can see it right here. Here's the 4.23, okay, and here's the 3.87. So you can identify the two numbers that you need in order to make a determination as to whether or not you reject that null.